Welcome students. So I am going to explain VSDL code for fulladder. So this is your diagram for fulladder. So what is fulladder? First you should know that is fulladder adds 3 bits A, B and C in, and after that it generates a sum and carry, that is here sum is sum and C out. Again, you know that in the logic diagram of fulladder, you can see that there is one XOR gate which takes 3 inputs, and there are 3 AND gates. They are taking 2 inputs, and one OR gate which takes output of these 3 AND gates, and after that it gives C out, that is carry. So this is the block diagram of your fulladder, where you can see that A, B, C in are inputs, sum and C out are outputs. Now we'll start with the Xilinx, the development of fulladder. So I will tell you the steps for starting your Xilinx. So in Ubuntu, first you have to create your directory, that is, suppose for example vsdl proc I will create here, and then I will open this directory vsdl proc. Okay, so in this directory you have to type command source /opt /Xilinx /Vivado /2016 /settings.sh. After that you have to press enter button. Okay, I'm not going to press enter, I already started it, and then type command vivado. After that press enter button, you will get your this window you will get your Xilinx will start, your Vivado HLX edition will start, and on dashboard you can see that there are different menus. So first is create new project, that you have to select here. So create new project, then press next button, then give the name here, that is I will give fulladder 1. I will give this name here. Okay, project name, then press next button. So project type is already selected, RTL project. Don't change the project type here. RTL is the real-time logic, and then press next button. Here the add sources window will appear. So remember that in VSDL, if you are going to design your program in Vivado Xilinx edition, so in that Vivado or in Xilinx, you have to create one design source file and another simulation source file. So in design source file there will be your hardware description of your entity of your circuit, their connections. Okay, so all that that design will be there in your design source file. So inputs and outputs, and in simulation source file there will be the testing of your test code of your circuit, that is what values you are giving inputs to your circuit, that values you have to initialize in your simulation source file, that is also called as test bench file. So remember about that. In next video, in next couple of time I'm telling you about that simulation source again. So here in this window you have to select target language VSDL and simulator language VSDL. Then click on create file. Here you have to select file type VSDL and give your name of file here vsdl.vst fulladder.vst. So press OK, then press next button. Then here don't do anything here, just press next button. Again don't do anything here, press next button, and here you have to choose your part. So I'm going to choose the part, that is, so we'll select any part here, and this part is the electronics part that you have to use for simulation. So that we'll select and then press next button and then finish. So this will create a project. So after creating project, it will give the window. The one window will appear, that is defined module. So here the entity name, architecture name you have to provide, but by default the entity name is taken as your file name is taken as entity name, and the architecture is given behavioral. So you can change your entity name, or you can you can continue with the same entity name, or also you can change your architecture name, or you can continue with this same architecture name. So I'm not going to change these names. Okay, now see in your diagram, in your full adder, see this diagram. So in this diagram you can see that this is your entity full adder, where you can see that A, B, C, in these three inputs are there, and you are getting two outputs, that is sum and C out. Okay, so in module we are defining our ports, that is our inputs and output ports. So A, B, C is these are our input ports, and these are output ports. So that we have to define here. So I'm going to define, that is first is A, second is B, third is C in, and they are having inputs, so they are used for input, so in is their direction. And next is my sum, that is output port. Then next is C out, that is my output port, and then press OK. So after this it will create a file fulladder.phd under your design sources. Click on that. So here the code is already created. You don't have to write anything here. The libraries are imported already here. You can see that. So it reduces your time. So in your architecture section, you have to define, now we are defining this, we are writing this program using structural modeling. So we are going to define modules, but before that we are going to define components here. So we will see the diagram which components we have to define here. So we can see that this is your logic diagram full adder, and this is the block diagram. So in this is main diagram for your full adder, abstracted diagram of your full adder. In this full adder, in this device, in this circuit, you can see that this is your internal circuit, where there is a XOR gate which gives sum, where there is a AND and OR gate combination which gives carry, that is C out. So in our program we have to define, we have to write write code for this XOR, for these ANDs, and for this OR. So we'll define code separate files for these all components, this XOR, AND and OR. So come to here, that is on design sources, and go here, there is a flow navigator. Under this flow navigator you will get so many options, and under this project manager there is add sources. In add sources you have to select create or design source. Okay, so create or design source you have to select, then press next, create file. Now the first component is XOR, which takes 3 input, so that I am giving name XOR3.vht. Press OK and then press finish. Again it will ask for a definition of the module, so don't change the entity name and architecture name. And now we know that first XOR gate is taking A input, is taking B input, is taking C in input, here C in input, it is giving some output, or I can take S here. Okay, so this is out. Okay, then this code is created, and this file is created here, this code is created here. So in this code, inside architecture, inside begin, you have to write the behavior of your XOR gate. Now you know that XOR gate do the XOR operation on all these 3 variables, that is A, B, C, in. So S is my output. So here type S less than or equal to, this is single assignment symbol, then after that A XOR B XOR C in. Okay, So this single line you have to try right here, then after that come to here. So now the first component we have defined here. Second component is and. So again go here, select design sources and again add sources, and here choose add or create design sources option. Press next button, then create file, and then here give the name and to .psd, because you can see that in that diagram and gate is taking two inputs, so that I have given and to name here. So and to.psd, press ok, press finish. Okay, again it will ask for definition of the module. You can see that it is taking two inputs, so you can take two inputs here, a b, and it is giving output y, so we'll take y output here and press ok. So this file is created here and to.psd. Again open that file and go here inside architecture, inside begin, and define here the behavior of your AND gate. Y is then equal to a and b. Okay, save it. Don't forget to save the file. So after that, the second component we have defined. Now the third component is what? That is our OR gate. So again go on add sources, then again choose add or create design sources, press next, create file, then OR3.psd. Now you can see that in that diagram the OR gate takes three inputs, so that I have given OR3.psd name. Press ok, press finish. Again it will ask for entity name, architecture name, and then port name. So entity name and architecture name, that you have to continue with that same name. And here I will give a input, b is my input, and then again c is my input, and then again my z is output here. So I will use here, okay, variable. Then again this file is created here, open it. In this file the code is already created. Again go in architecture and begin. So here in begin you have to define false set. There is my output. So do the signal assignment. Now we know that OR gate performs OR operation its inputs on its inputs. So A or B, A or B or C. Okay, so this is defined here. Now three components we have defined, their behavior we have defined. Now come to our main program, that is fulladder.vsd file. So in this we have defined our entity, that is fulladder, and their inputs and output ports. Now come to here the architecture inside declaration part. This is your declaration part. Okay, so in declaration part, okay, so this is your declaration part, and for in vhdl program, you know double hyphen is used for comment. Okay, now I will try. Okay, so we have to do declaration. So in declaration part, generally we know that in declaration part we are defining our components. So there are three components: XOR, and OR. So first XOR 3 component is there. So I will define XOR 3 component here. So I am going to copy same ports here. So the same ports I am going to copy. Okay, so copy it here. So save it. The next component is and 2. So remember here your component name and this file name. In this file the entity name is XOR3. This should be same. The file name should be same and the entity name should be same in this file, and that same name you have to use here for component. Otherwise it will not use this file, this entity in your main program. So XOR3 that we have given. So same and2 is the next component. Here is and2 file where and2 entity is defined. So end component. So in between this again I am going to copy these ports because these are the same inputs and outputs in my component, so that I copied here. The third component is R3 in component. Okay, so in this I will copy the port of this R3. Okay, so sorry for the mistake. Okay, so I copied this, so we'll copy this. Okay, so I copied this and I will paste here, so that the ports are same. Now the components are defined here. Okay, so now we know that the signal is here. There is the use of signal because we know that here the XOR is taking inputs and directly giving outputs, so there is no in between other gate available in that connection. So the direct connections are connected to XOR and XOR is giving output. But here you can see that in between this OR and this middle signal is there. These wires are there, these connections are there. So how to define these wires, the wired connection in your program? Because it is taking inputs, but what about this output? How it is giving to the OR gate? So we'll assign this connection, we'll declare it as a signal. What is signal? Signal is a wire connection. So I will assign P signal, P name to this, Q to this, and R to this. So it will be given as input here for OR gate. So we'll define here, declare here, signal is the keyword for that. Signal P, Q, R, and their type is std_logic. Okay, so this is our std_logic, where you can see that 4 values are allowed of 0, 1, you set high impedance and don't care. So in begin section, what you have to do, that is you have to do port mapping. The port mapping is very important because for port mapping you are doing all these port connections. Sorry, extremely sorry. So here you can see that in logical diagram we can say that we have drawn these connections, but in program how it is going to determine these connections. So with the help of port mapping we are doing all these connections with each other. Okay, we'll connect all these gates with each other. Okay, so see, we'll do that here. So I will give label for these gates. So I will give label for XOR. I will give X1 label for this, and I will give label A1 for this, A2, and for this A3, and for this OR I will give O1 label. So for every component I will give a label here. So first is X1, that is my XOR gate. So XOR is my component that I have to map, and I will use port map here. So I will map what I will map here, that is my input is A, then my second input is B, third input is C in, and then output is sum. Okay, then A1 is my first AND gate, where I will use AND 2 entity or my component port map. Here you can see that we are taking A input, we are taking B input, and we are getting P output. Okay, then E2 is my second AND component that I will do port mapping. Here I am taking B input, I am taking C in input, and then I am getting Q output. Okay, then here is my third AND gate, and again I will use AND 2 port map, and 2 is my component. Here I am taking A input and then C in input, and I am getting R output. Okay, so and here last component is O1, that is my OR gate, where I will take OR3 is my component name, port map. Here I will take P, Q, R, C out. Why? Because PQR, these are the outputs of AND gates. They are given as an input to the, here you can see that in this diagram, this P, Q and R, these are given as an input to this OR gate. So that I mapped with that component. Okay, so now this part is ended here. So we have designed our program, we have completed our design sources. You can see that under this design sources, this fulladder.vsd is my main file, main program. Under that you can see that XOR3, N2, N2, N2 and OR3, these are the components. Okay, so now come to the simulation source. Okay, now we have to define simulation source. So click on simulation sources. So after that, here is in left side in your project manager, there is add sources. Click on it. Here choose add or create simulation sources. Click on next, create file, and file type you have to choose vhdl, and then give full add underscore tv.vsd file name. So why underscore tv? Because we are just considering that this is test bench file, so that we can give that file name here like that, full add underscore tv.vsd. Press OK and then press finish button. You will get here define module, but now in test bench, remember that in test bench we are not defining entity. Clearly you should remember this. Okay, so press OK here, don't give any input, and press S here. So you'll get your code created here. Your file will be created under simulation sources. Go in this directory, simulation sources, again in sim1. Here is your fulladder underscore tb.vsd. Click on it. So this file is generated here, created here. So don't you should go directly in architecture, and here change your architecture name. Okay, so give bench, or you can give any other name, but here in your declarative part, this is your declarative part. Okay, this is your declarative part. So in declarative part, what you are doing, again we are going to define our component. Now we are having a single component, that is full add in component. Why I am taking full add? Because in your first file this entity name is full add. So this component you are defining in your test bench here, you are declaring here. So here full add is my component, and port I will copy from this full add dot vsd file. Okay, so copy it here, paste it here, save it. This is my single component, and then I have to declare my signals, signal a comma b comma c in comma sum comma c out colon. My type is std underscore logic, because here these are the only signals for full add component. Okay, so after that, in begin, what you have to do, that is you have to do the port mapping first. So I will give UUT the name for my label for my full adder. Then I will use full add the component name. Then I will use port map. Okay, so here what will you do, that is you have to do here port initialization. So you are initializing same port here, so A with A. Then for your convenience, I am showing this every port initialization new line. So C in with C in, sorry, give comma, sum with sum. Okay, C out with C out. Okay, so Q comma here, don't give semicolon, and after finally semicolon. Okay, so this is your port mapping. After that, you have to use stimulus keyword and process keyword. This is our now we are using behavioral modeling here. We are giving the behavior through our test bench. Now in this, there is again begin keyword. So after this, you have to whatever the truth table of full adder. That truth table, in that truth table, whatever inputs are taken, that input values you have to initialize here with your inputs. Okay, don't initialize output in your this section. So see what I am doing. A less than or equal to, I am initializing single value, initializing here like this. P equal to in 0. C is 0 because in truth table we are taking these values. After this you have to provide wait for 10 picosecond time, because in wave diagram you have to give time interval 10 picosecond in between among every wave. Okay, so that we will get a proper wave diagram. So we'll copy this. I'm not going to type it again because we have to change only values, and every other part is very same. So I'm going to change just values. So again copy it here. The next input is 0 1 0. Okay, and then again 0 1 1 1. Here again 1. Okay, so again here the next input is 1 0 0. So 1 0 0. But we have done mistake here. We have done mistake. What? That is, this is our C in, not C. So this is C in. C in. This is C in. Again this is C in. So copy it again. I will copy this because C in should be there. Okay, so this is 1 0 1. Next signal or next value, next full table value. The next is 1 1 0, and finally we are coming to the end, that is 1 1 1. So 1 1 1. Okay, so this. Okay, now come to the last. Here remove this wait for 10 picosecond and make it is 0 0 0. Okay, and here end wait, and here process block, and end your architecture block. Here remove this behavioral because now we don't have that behavioral block here, behavioral architecture name. So we can again we will check it whether it is correct or not. 0 0 0 1 0 1 0 0 1 1 3, then 4, then 5, then 6, and then 7, and again 0. Okay, so this is defined here. Now I'm going to synthesize this program. Okay, so after this, like your programming or program compilation, this program you will synthesize. So we'll do the synthesis here. So in left side under this flow navigator there is synthesis option, and again there is run synthesis menu that you can click on that menu, that option. So run the synthesis. Have some patience, it will do a little bit time. So now you can see that synthesis failed. So we'll see the message what happened here. So it shows a valid license was not found for feature synthesis, and okay, why this program arise? Because whatever license we are using, in that license they are not providing the license of all the parts. So we have to change our part here. So how to change it? So don't take any tension. In exam you will not get that difficulty. I will provide you the part name which you have to select, but here I will tell you just one. You will get idea about that how to change it. So here in project summary, you can see that in project summary, click on this project part, and under this here click on browse for project device. So here you can check for other part. Okay, so I am going in upward direction. So I am taking that so this is XA7A15 TCS G3242L. This is working part for me. So I am taking it and pressing apply, and then OK. So again we will do the synthesis here. So synthesis is running now. Synthesis is running. So it is running. So it is taking a little bit time, but don't get confused. It is doing compilation like your program. So now, okay, we have successfully synthesized the program. Synthesis completed successfully. Run implementation. Open synthesize. Design and view reports. So don't select anything here. Just press cancel button. Okay, and then go here in simulation in flow navigator. That is simulation menu. Under the simulation menu, there is run simulation option. Choose run behavioral simulation. Now it will create wave diagram. Now I am going to minimize this, again this, again this. Okay, so I am going to drag it, so we will get complete wave diagram here. So already it is executed, but it is executed like this, 1000, 1 lakh ps. Okay, but we want in 10 picosecond interval format wave diagram. So here there are three options. You can see that restart, then run all, and run for 10 picosecond. So click on restart, so it will get into the first, that is 0 picosecond. So right click it here and press out, and again 3 times you have to press out. So it will zoom out and it will give the 10 picosecond interval wave diagram. Okay, here again change picosecond time and then give 10 here. Now we have to see our whether we are getting our output or not, we are getting our correct output or not. So first, you know that ABC in are 0 0 0, so click on it for run for 10 picosecond, because for every 10 picosecond we are getting our output. So when you know the truth table and its output, so there if there all 0 zeros are inputs there, and it is given sum and carry 0. You can see that here all the signals are low here. Okay, then you can see that when it is 0 0 1, here now signal is high for C8. At that time we are getting sum 1, the signal is high, and carry 0, that is Cout is now low here. Again you can continue this process until your sum is okay. Finally you can see that here is 1 1 1, input is all inputs are 1, that time you are getting sum 1 and carry 1. Okay, you can see that all the signals are higher, and finally you are getting your signal 0. Why? Because in simulation zones finally we have given our